Hey, this is Brock Lemire's Embedded Systems Design. We are looking at the SPI peripheral on the MSP430, and in this video, we're going to look at how to accomplish receiving data as a master, and then we're going to do an example where we drive data into ourselves, essentially. Okay, so remember when you're receiving data, you, as the master generates the clock. So you are actually going to still have to set up the clock to have the right bit rate that you want and also the right polarity. And then somebody out here, the slave, is going to send you data, but you have to give them the clock. They're going to have data sitting in their transmit buffer, but it won't come out until you give them your clock. And so in order to do this, if you're working with an external peripheral, you have to actually provide 8 clock cycles to get the data. So the way you do this is you simply write a dummy byte of any value to your own transmit buffer. So you're going to transmit out junk, essentially. I would recommend just writing zeros. And then the slave has to know that as the clocks that come in and to pump out its information, it's also going to receive a dummy byte. And so it just needs to know that the byte that it receives is garbage data and just ignore it. But that's how you essentially initiate a receive, is you just write something to your transmit buffer, and then 8 clocks later, you're going to have information come in on your own receive buffer. And then when the receive buffer, basically it'll shift in on the 8 clocks that are generated by this. And then as long as you have the same framing option set up, everybody has to have the same framing option set up, it will then transfer into the receive buffer, and then guess what? It will generate a flag. And so that's whenever you receive, always remember you have to rely on interrupts to know what's going on. Even though you know that once you write to your transmit buffer and cause the 8 clocks to go out, you don't necessarily know exactly when they're going to be done. So you're always going to wait for that receive flag to be set up. Okay, so we're doing a receive now, and so you're like, well, what interrupts do we have available to us? Well, we have a RX IFG flag, which basically asserts whenever you have information that's ready to be read. What's cool about it is that when you read from this buffer here, this RX buffer, it will clear the receive flag, so you don't necessarily have to worry about clearing it a lot, although you can. But this receive also shares with the transmit. Okay, so you notice that they're both at the same vector. So if you're going to have transmit and receive functionality, you have to actually have code in your interrupt service routine that handles that. Okay, we are using the slave out master inline, which we've set up before, but just remember that when we do that, it's a dedicated pin on it's a dedicated signal in the SPI peripheral, and we just have to tell the port function select registers that instead of using the ports, use this slave out master in. Okay, so here's an example. Let's do this example where we set up the SPI system as a master, and then we'll transmit data out over our own master, and then we'll receive it into our receive buffer. And so what we're going to do is we'll actually just put a connection between our master out and our master in pins on the launchpad board, and we'll watch the data go back. And so here's we're going to create kind of a dummy program. So here's what I want to do. If you press S1, it will send out 1-0. And to verify that the receiver is actually getting different information each time, because if we only had one button press and one piece of information, we'd never see it change. So it'd always look like 1-0s in the receive buffer. So we'll send 2 different types of information. So we'll send, if you press S1, it'll send hex 10. If you press S2, it'll send hex 66. And just for no other reason than to write an interrupt service routine for the receive, when data is received, the interrupt service routine for the receive flag will light up LED 1 when it sees 1-0, and it'll light up LED 2 when it sees 6-6. Okay, so we'll basically press S1 and LED 1 will toggle, and we'll press S2 and LED 2 will toggle. Now that alone is interesting. That will show that we can toggle LEDs, but in order to know that information is actually going back and into the receive buffer, we'll have to use the debugger and actually look at the registers. Okay, so here's the setup. What we're going to do is we're going to wire our slave in master out directly to slave out master in, and like I say, we'll do that with a jumper. So let's get started. So fire up CCS, and we'll start a new project. So I'm going to go File, New, and let's call this C_SPI. SPI underscore RX1, our first receive example, and we'll just receive a hex byte on A0 and blank C, and we're off and running. Okay, so this is going to be one of the longer programs that we've messed around with. So in order to speed this up, I'm going to do a lot of copy and paste of my code, not from prior code, but within the code, because a lot of the setup is redundant. But anyway, if you fall behind, just hit pause, and I'll try to compile a little bit more frequently so I catch typos. Okay, first and foremost, set up the A0 SPI. All right, first thing I need to do is go into UC, Universal Serial A0, control word register 0, and I need to put this into software reset. So I'm going to say UC software reset. I set that bit to put A0 into software reset, and now I can configure everything. First, let's do the clock first. So go into UC A0 CTL word 0, and I'm going to choose SM clock. UC SSEL underscore SM clock, and this is going to choose SM clock, and that's equal to 1 megahertz. But then let's divide it down to something that's manageable. So UC A0, and I'll go into the bit rate word register, and I'll go ahead and drop a 10 in there, and that will set prescale equal to 10 to get S clock equals 100 kilohertz. So that's our S clock that will pump out as master. Let's now go ahead and put the system into, let's put the peripheral A0 into SPI mode. So I'm going to go into UC A0 CTL word 0, and what I'm going to do is I'm going to set the UC sync bit. So I put it into synchronous mode, which is put into SPI. As opposed to asynchronous mode, which would have been the UART on A0 and A1. And let's put it into master mode. So UC A0 CTL word 0, and I do that by setting the UC MST bit. So set as master, master. Okay, so now that's essentially ready to go. Really, that's all we're going to do. So we're going to accept the default settings for clock polarity and also the framing options, which is LSB first 8 bits. And so now we're going to do configure the ports. So configure ports. That was actually pretty straightforward because we'll do the interrupts in a second, but that's about all you need to do. That is all you need to do. We just need to take it out of reset, and the A0 SPI is ready. Okay, so first and foremost, we're going to do 2 LEDs. So we need to go out to remind ourselves we're going to do... let's see, let's do this. Let's go set port 1 bit 0, which is LED 1 to output. Okay, and we do that by going port 1 direction, and let's set bit 0. Okay, so that's that. And then I'll go to, let's make it off initially. So port 1 out. What I want to do is I want to clear bit 0, and then that is LED 1 equals off initially. And now here comes some copy and paste. So here I'm going to do this, copy and paste. And I'm going to do that because now I'm going to set up LED 2. So now I'm going to go to port 6 bit 6, which is LED 2, and I'm going to do that. Now what's different about port 6 bit 6 versus what I did for LED 1? Well, first of all, we need to go to the port 6 direction register and change bit 6, and then same thing down here with initializing port 6 out and clearing bit 6. So copy paste, I just set up LED 2. So that was pretty cool. And now let's go do the switches. So I'm going to go ahead and set up the switch. So I want to do this. I want to go set port 4 bit 1, which is switch 1 to input. Okay, and so now I'm going to come in here. I'm going to go port 1 dir, and what I want to do is I want to clear bit 1. Okay, so that's port 1, not even close, port 4, port 4 direction, and I'm going to clear bit 1. Okay, now let's turn on the resistor. So I'm going to go port 4 REN, and to do that I set bit 1. So this is turn on resistor, and then I'm going to go to port 4 out, which is using the secondary function of port 4 out when you're using it as an input. We set bit 1 of that register. And what that does is makes resistor a pull up. And finally, since we're going to do an interrupt on this to trigger off the switch press, I go to the interrupt edge sensitivity, and I'm going to set bit 1 to make sensitive to high to low. Okay? All right. So let's take a look at that. Port 4, bit 1, 1, 1, 1, 1, and then make sure all your tildes are in there, and we'll go ahead and save that. And now let's set up switch 2. I'm going to copy those 4 lines of code and watch what I'm going to do. Switch 1 is on port 4 bit 1, but switch 2 is actually on port 2 bit 3. And if you ever forget where these are, just look at the launchpad board because it says it right on it. It's got the little silk screen that tells you. And so now port 2 bit 3, what do I need to do? Well, all I'd really do is I need to change my configuration registers to port 2. So those are all updated, and instead I need to change the bit that I'm messing with to port 3. And holy cow, that was quick. Okay, so now that's good. And so what else do we need to do with the ports? Well, I need to set up the peripheral, the SPI peripheral. So I need to remember that port 1 bit 5 is equal to S clock. Okay, and I need to configure the port 1 select registers, and there's 2 of them. There's 1, and I'm going to clear bit 5. Okay, so port 1, select 1, and I clear bit 5, and let's do this. I'm going to copy and paste this one, and now I'm going to set bit 5. Okay, and so what I did there is this register has to be 0. So what I'm trying to do here is I need to say port 1 select 1, port 1 select 0. Those 2 in conjunction need to be 0, 1 in order to turn bit 5 into the S clock function. Okay, and so that's pretty good. Yeah, that's pretty good. That looks right. So now let's do this and copy and paste that, and now let's do port 1 bit 7, which is slave in master out, and the only difference here is that instead it's still the same port 1 function registers, but I'm changing bit 7. And now the next one is copy and paste this, and I'll go down here and I'll go boom, and now this one is the master in. So this is on bit 6. So when I come in here, this is now actually slave out master in. And so for this one, the only change is I change this to port 6. Okay, so now the ports are set up, so let's turn on the I/O. So power module 5 CTL0, and I need to clear the lock low power mode 5 bit. So this is turn on I/O. At this moment, let's compile this and figure out if we had any typos. Okay, there's a lot of stuff going on here, so let's go project, and I'm just going to build project. And that'll do a quick compile of it. Look for errors, and let's see what I got here. Error. Okay, we got a couple errors. Let's get that. Line 14. Yeah, got a semicolon. Okay, got that. And then anything else? Let's see. Let's save, and we'll go project build. Okay. All right. So I got my configuration registers set up. And in reality, now I'm ready to turn back on the system. So now I'm ready to do this. I'm ready to take this out of software reset. So I do that by clearing it. So I copy and paste that, and I change this to a clear. And then that is going to take A0 out of software reset. Okay, so that is we've set up the SPI peripheral. We've set up the ports, and it's ready to go now. And so now we're at a point where we need to set up some interrupts. So I'm going to set up my interrupts, and I actually am going to set up 3 interrupts. One for switch 1, one for switch 2, and one for the receive flag. Okay? And so let's do this. I'm going to go ahead, let's set up enable port 4 bit 1 IRQ, and this is going to be for switch 1. Okay, and so to do that, first thing I'm going to do is go port 4 interrupt enable, and I'm going to set bit 1. And so right there, what that did is it did the local enable for port 4 bit 1, which happens to be switch 1. Okay, and let's go ahead and clear the flag. So port 4 IFG, and I'm going to clear bit 1. So I come here and we'll go ahead and clear flag. Okay, all right, so that looks port 4 bit 1. That looks good. I enabled it. Okay, so now let's do switch 2 via copy and paste. So I copy and paste that. And remember that switch 2 is on port 2 bit 3. So port 2 bit 3, and that's going to be switch 2. And the only difference here is I changed my register to port 2 interrupt enable and port 2 flag, and I got to remember to change it to bit 3. So now that local enable set up. And now I need to turn on the interrupt for the A0 SPI. So I go into the UC A0 interrupt enable, and I'm going to set the UC RXIE. So that is now enable SPI RX interrupt, IRQ. Okay, so that's cool. And while we're here, since we're clearing flags, we don't need to do this, but I can't stop. A0 IFG. Go ahead and clear. So I'm going to clear out the UC RX IFG. Okay, it's cleared out of. It's clear out of reset, but I don't know. I cleared the flags here. I want to clear it here. Okay, so let's check the typos on there. Let's save. Looks pretty good. So let's go ahead and turn on all the maskable interrupts by doing the enable interrupt function. So this is enable maskable IRQs, and it should turn purple. There it goes. Okay, good. And now I'm feeling pretty good. And my main loop is going to do absolutely nothing. So that's that. Okay. So do nothing. Okay, so that's good. Let's go ahead and clean up our typos. So build project. If you ever hit that build all, you're in for a bad day. Because it builds every project in your project folder, and it takes a long time. Okay, so now all the functionality in here is going to be done with interrupt service routines. So now I come down here, and I'm going to go, here's my section for interrupt service routines. So let's do the button. Okay, so if I press button 1, I want to set up a interrupt that does this. I'm going to go pragma and tell the compiler, excuse me, please set up the interrupt vector table for port 4, please, and its name is vector. And go ahead and put the starting address of the next routine into that vector. By the way, this routine I'm giving you is going to be an interrupt service routine, so please return from it using a RETI instead of RET. Thank you. And of course, I'm not going to pass anything in or out of this interrupt service routine. Instead, what I will do is simply, when I get to this interrupt service routine, somebody pressed button 1. So this is ISR for switch 1. Okay, so what did we want to do? Well, when we press button 1, I want to transmit out hex 10. Okay, so the way I do that is this. I go UCA0 TX buffer. Okay, and I'm just going to dump 0x10 in there. So send 10 out over SPI. So I'm transmitting that. And maybe TX would be better. Now that's going to go out, and we're going to wire that up to our receive buffer so it'll actually get it. Remember, this is a button press, so I'd have to clear the flag here. So since I don't want to type that anymore, let me go up to right here and clear the flag. I'm going to go right here, and I'm going to clear this flag. And there's the first interrupt. So let's go ahead and build that, because we're going to copy and paste that. So life is good, no errors. Now watch this. I'm ready to now do the interrupt service routine for switch 2. Copy, paste. What's different? Well, remember, switch 2 is on port 2 bit 3. And so here I'm going to change this to the port 2 vector. So I'm going to set up the interrupt service routine for port 2. I'm going to change my interrupt service routine name to port 2 switch 2. And what is its functionality? Well, it was going to send 6.6 out of the SPI instead of 1.0. So all we're doing here is I'm going to transmit 6.6 out over SPI. So I just changed what I dump in the transmit buffer, and then I have to remember to clear the flag the right way. So I got to clear port 2 bit 3, and that's it. So now I've sent And so really now the only thing I need to do is I need to write the interrupt service routine for my receive flag. So what do I want to do when I see something come in on the SPI receive buffer? Well, let's set up an interrupt service routine by saying EU SCI underscore A0 underscore vector. And this means there's data is in buffer, okay? And it's not just buffer, it's in A0 SPI buffer. Now, that's cool. We want to do something. So I'm going to do interrupt, and I'll void it. ISR, we'll call this EUSCI underscore A0, and ISR, EUS, okay, and we're not passing anything in, and we'll go ahead and bop that. Okay, so now here we are. What are we going to do? Well, this is kind of interesting. It's like I want to grab what's in the receive buffer, okay, and I want to do something. I want to light up an LED. So now I'm going to set up a variable, RX data. What I'm going to do is I'm going to grab UCA0 RX buff. So I just now read RX buffer. Now I know that the way that the debugger works is if you make this a local variable, you can't see it in the debugger. And so I'm going to make this a global variable. So to do that, I'm going to come all the way up to the very top, and before my main, I'm going to come out here and I'm going to do int RX data. Okay, so that now makes that a global variable. I didn't need to make it a global variable, but it helps when I try to debug this so that I can actually see it in the debugger. And so now we're sitting here and we got that. And so now you're asking yourself, what am I going to do here? Well, if you remember, well, the whole point of this program is if RX data equals 0x10, then port 1 out is toggled. So I do a bitwise exclusive OR, and this will, if it's at, toggle LED 1. Okay? And then I'm going to copy this, and I can come down here, and then I'm going to do an else if. So watch this. I'm going to do this. I'm going to come over here, copy this whole thing, and I'm going to go else if RX data equals 66, I'm going to toggle LED 2, which happens to be on port 6, bit 6. And now I'm going to toggle LED 2. And now we hope we have all this set up. And the reason I do it as an else if is that just in case something else came in, I don't want LED 1 or LED 2 to toggle. I only want to do it when I see these two pieces of data. Okay? And that's really all we need to do. Now notice I'm not going to clear the flag in here because if I read from the RX buffer, it does clear the flag. Okay, so we're ready to go. So let's go ahead and just full-blown debug this and check for typos, and then we'll test this program out. So we got one typo. Where is it? You probably saw it. Unrecognized directive, line 80. Pragma. Make it a pragma. Pragma should turn purple. There it goes. All right, and then let's see any other typos. All right, looks like it's going. This is a monster program here. Okay, we're ready to go. Okay, so let's take a look at the board. So here's the board, and I need to connect port 1 bit 6 to port 1 bit 7. These are 10th inch header pins, meaning that each pin is a 1/10 of an inch away from its neighbor. And so I can actually use one of these jumpers to connect those two. So go ahead and borrow a jumper from here. This right here is a light sensor, so you have to have the A to D and the D to A working to use that. So we're not using that right now. So if you pluck one of those jumpers off, you can just put it right here. And see, I got port 6, bit 6 connected to bit 7, and so that'll connect the master out to the master in, and that will allow me to shift information into myself. Okay, so that's how you do that. All right, and so now what I'm going to do is let's go ahead and run this and see if it kind of does anything yet. So I go ahead and hit run, and I'm going to press switch 1, and LED 1 came on. If I press it again, LED 2 or LED 1 went off. So I'm doing this. What is happening is I'm actually, every time I press it, I'm shifting hex 10 from master out into master in. And so it receives information, the RX interrupt fires, RX flag is asserted, and it's working. And so then now let's check if I can send 66. Well, look at that. That's pretty cool. So now if I press switch 2, switch, it's sending 6.6, and the receive flag goes into that interrupt service routine and goes, hey, I received something different. So it's working. So this is working. The only problem with it is that you can't see what's going on. You might have just downloaded a different program. So let's go in and look at the buffer. So I'm going to go ahead and press switch 1. And so the receive buffer is just received 1, 0. I'm going to go ahead and pause the program. And so now what I want to do is I want to go in and I want to see information. In fact, actually, let me do this. I'm going to turn off optimization. So let's go into project properties, and then we'll turn off optimization. So I want optimization and turn that off, and we'll see if we can see the the actual variable RX. So here we are, and it downloads. I run. Okay, come out and test it. Switch 1. I just sent 1, 0. I'm gonna go ahead and pause the program. Okay. So now I'm sitting here and go ahead and step once. So I step once, it didn't work. But anyway, let's go into the registers. I want to go into, I'm going to come down to the serial system, the EU, Universal Serial Communication System interface, and I go to A0. So I want to go into A0, and I'm going to open that. So I expand that a little bit. And I'm going to come down here, and I'm looking for the RX buffer. So here it is. So there's the RX buffer. So that's pretty cool. There's 1, 0. Okay, I got 1, 0 in there. So now if I run, okay, and I go ahead and press S2, now something different should be in there. So I'm going to go ahead and pause it and see what's now in there. And it's 66. So that's pretty awesome. And now you can, I did that without even setting a breakpoint. If you wanted to do that a little bit better, you could come in here and come down to your interrupt service routine, and let's see, go into your interrupt service routine, and right after you read from RX data, put a breakpoint right there. So I go ahead and hit run, and now if I press S1, it breaks and 1, 0's in there. Now if I run and I press S2, it breaks and 6, 6 is in there. And so this is awesome. Awesome. Okay, it worked. We did it. Oh, by the way, where's RX data? Well, since I made it a global variable, they actually put it at the beginning of data memory. So if I go to the memory browser and go to 2000, I can see RX data. I don't know why it's not showing up in variables, but I've found that these global variables, they usually go at the beginning of data memory. So here now is RX data. So now watch this. If I do this, I go run and I press switch 1. I see the RX buffer get 1, 0, and I get RX data, which is in data memory, also gets 1, 0. And let's do it again. So I press that and I do that, press switch 2, and now, well, I had to run it. So I do that and I hit switch 2, and now it's got 6, 6. Notice that also the transmit buffer has the same value. That's because I'm sending 6, 6, I'm receiving 6, 6, and vice versa. Holy cow, that was a long program, but that was awesome. Okay, you did it. You just sent data out of SPI master and received data into the receive buffer as a SPI master. All right, congratulations. As always, support my channel by subscribing, and see you.